Oh, really? Oh, it's so dark in here. We're definitely happy.
Start snoring like that. How are you told us?
Okay. Hello. I hope you all had a great lunch. We're going to try and make up some time. Who knows? Maybe we won't. Maybe we will. I don't mind moving a bit slowly. I'm here all week. If anybody needs help, continuing to learn, no problem. Yeah. If you could go ahead and open Julia back up into the same QNumerics project. The empty folder with just the project.toml. And if you would like to participate in the quizzes, there's the information on how to join the next set up there on the board. Hopefully there is a new and improved dashboard. I don't know how it works, but we shall see. Hopefully, I believe it should show the time at the very least, so people aren't getting kicked out in the middle of their answers. All right. So we spewed a lot of syntax at you last time. I'll remind you of this a few times again and again, but there really is only one fundamental unit of computation in Julia, and that is the function, right? Foo of X and Y. Everything else that we talked about, broadcasting, indexing, all of that lowers down to function calls. So if I take, for instance, I should probably be, can everyone see? Oh, I made it too big. All right. If I do A equals rand 2 of 2, that gives me a 2 by 2 float 64 matrix. If I do A sort of 1, 1, right, that's the upper left-hand corner. And we have these nice macros, which again, I mentioned, I'll have a list of sort of tools for you that can help look at code, inspect code, figure out what's wrong. But one of the classic ones that we like to use a lot, especially those of us who are more familiar with the internals of computers, like to use are the code underscore blank macros. So I believe there's 4 of them. The first is code lowered. So that's where we take syntax like A11 and we transform it, ignore some of this stuff, and we transform it into, we essentially desugar it, right? This A bracket 1, 1 is what we call syntactic sugar. And so we take that and we turn it into a function call, right? Base.getIndex of A, and we take the first, this argument here. This is a little bit hard to read, but this essentially is you can think of these percent sign numbers as variables. They're just assigned to once. So, this percent sign 3 is assigned to a bounds check. But in general, the core part that I want you to see here is that this A11 syntax is just the get index function. It's the same with broadcasting, although good luck if you really want to explore the internals of broadcasting. It's kind of the worst part of Julia. But all of this sugar really does just become normal function calls at the end of the day. So if you're ever confused, just know that you can write the same function without any of that stuff and just write it with function calls. All right, figure this. It didn't clear at all. So I want to put some of these things together into some real world, I'm not going to say applications. These are far too small of functions here. But the first one is the Fibonacci function. Let me zoom in. And fib dot 0 to 10. And this should give us the Fibonacci numbers. I didn't check it, to be totally honest. What we're doing here, we're assigning A and B to 0 and 1. We talked about that before. This is essentially two tuples on either side, right? It's the tuple A and B and the tuple 0, 1, and we can unpack them. This for loop might look a little strange because we don't actually care about the index of the for loop I. So we can just put a blank, underscore. Since we're not actually indexing into anything, we're just doing some math repeatedly. You can also do recursive calls in Julia. There's no problem with doing that, but in general, recursion is not the fastest thing in Julia. It's a little bit slower than recursion in the functional languages. They have something called tail call elimination. But you can still write things like that perfectly fine. This Fibonacci recursion function, checks some constraints and then either calls the left-hand side or the right-hand side, subtracting 1 or 2, depending on which side it takes. Next, we can do the quadratic formula. Instead of square root, you might do s equals square root here, and then you can do b squared minus 4ac. You'll notice the juxtaposition multiplication that we talked about earlier, and we can use the Unicode here as well. But we don't have p there anyway. This quadratic function is, just like all the functions we've talked about so far, is duck typed, right? So if we look at the methods, which I'm just going to once again ignore right now, what that semantically means, we have A, B, and C. There's no types attached to them. Julia doesn't actually care what type you put in there, but once you put a type in, it will compile that function using that type, and it will be quite fast. So for instance, we can take, the quadratic formula of complex numbers. The only reason we could do that, of course, is because these arithmetic functions are all implemented for, complex numbers, real numbers, many of them for integers. So let's see. One thing that Alan Edelman, one of the creators of Julia, was very frustrated about a long time ago is that they took the mean function out of Julia. It's in statistics packages, but it was removed from Julia base because there are sufficiently mathy people who couldn't really agree on what mean meant for different things. So we don't have a mean function in Julia, but it's perfectly fine to just sum things up and divide by the length, right? And now we have regained our mean function, and we can apply this mean function to pretty much anything that is iterable, right? We can do a range, we can do a vector, we can do a tuple. All of those work just fine. You can even do a step range, right? Like that. Of course, that's the same thing because the bounds on either side are the same and it's evenly spaced. But yeah. We can move on to some more complex functions like Newton's method. So this is probably, other than reduce and map, right? Recall reduce takes some iterable and applies sort of a reduction function. So it'll add all the values together. It'll maximize, do the pairwise maximum across them. You could divide each value by the next one. So that was one example of a higher order function, a function that takes a function. We have the same thing here. We can have a function that takes f and f prime, the derivative of f, and a starting point. And here's where tolerance comes in. So we have, one of our first mentions of tolerance. I mentioned before that we have the approx shoot, you can't see that at the bottom, can you? You have the approx equal sign, and you can also do isapprox and a couple other comparison functions that also take tolerance. But we can pass something like x squared minus 2, and then, the derivative of that. And notice that these are anonymous functions here. We don't plan to reuse them. And because all of these things, like I said, are duck typed right now, because they apply perfectly well to most number types, you can do this with complex numbers. You can do this with all sorts of other things. Excuse me. We can do the classical estimate of pi with the Monte Carlo method. You can see here we do a broadcast statement, and then we sum over the results of that. And then this is a scalar, so these don't need the broadcasts. This is just normal scalar multiplication and division. You see this syntax here. This is just a nice way of writing 100,000. You can't use a comma because that would be 100 and 0. So if you want to sort of separate things out into digits when you're writing really, really big numbers, you can use an underscore, and that essentially is the sort of comma that we use to separate out large numbers. Excuse me. And finally, we can use some of those string functions that we talked about earlier. So the first thing that we do for word counts is we construct a dictionary, string to integer. One sec, let me grab some water here. The next thing that we do is we split the text into individual words. Split, I believe, can take sort of the delimiter that you want to use to split, but in this case, I believe it just uses the space. Then we iterate over each of those words. And the first thing we do is we strip away all these symbols, we strip away commas, we strip away question marks with this function. Then we take the result of that and we make it lowercase to clean it up. If it's empty, we no longer have a word, right? We just had a comma or something that got lost once we stripped it away. And we can use the short circuiting form to say, if it's empty, then just continue on to the next iteration in these words here. Otherwise, we can use the word to index into our dictionary, and the get function is one of the ways you can access a dictionary with a default. So we look for the value or the word in the dictionary. If it's not already there, we return 0, and then we add 1 to it. So those are some minorly more complex functions than the things that we've looked at so far. But that gives you a good idea of what sort of real Julia code looks like. A lot of functions are fairly small. We have pretty powerful verbs in Julia. So ideally, we don't have super long functions where you're doing busy work, essentially. And you can often express a lot of mathematical ideas like Newton's method fairly cleanly. Even some pretty significantly optimized versions of Newton's method in Julia are pretty legible. All right. We've got some people connected. So I'm going to ask a few questions. These have a bit of a longer timer. They're essentially going to ask you to write some functions. You can write the function in the quiz thing because you're just going to write the whole function out and it's going to test whether or not the function was correct. Yeah.
A little quick question. I just noticed that in this Newton method, the point was that f and f prime are two function arguments to the function, right? I also noticed earlier that prime was an operator you used to do complex conjugates. I just wanted to know when.
These are different. This is something you shouldn't really do in professional software development. I believe these are different symbols. Let's see here. So yeah, that's the prime symbol, literally. It's a LaTeX symbol. Whereas the adjoint is literally just the comma. Yeah, it's bad. This is not how you would write it if it was safety critical code, but it's math code, so nobody really cares. Yeah, sorry about that. All right. It's gonna work.
Oh, yeah. Sorry. I'm just like, I'm not sure. It doesn't have anything. Okay.
I'm just going to follow on along a little bit behind where people should be, so nobody falls super far behind.
Using the student.
You said it, I was a student.
But
Oops. Apologies.
because you might not be so.
Remember, you can test this outside the REPL. You can write the function and then just type in the function name into the quiz. Should be some examples of right here.
Yes.
Started evaluating your first.
I can't listen anymore.
Yeah. It's like they're very. That's cool.
Alrighty. So this function here is the correct one. Did anybody have any questions getting there? Did anybody have any problems they didn't expect to encounter? Go ahead.
Getting an error for end. I just couldn't understand where to use end.
Yeah. So end comes after things that behave like blocks. So I didn't really specify, so that's on me. The first big one is functions, right? So function, the name of the function, the arguments, and then end. Those are the things that are required for functions. While is the next one, and for, so loops. After that are sort of the specific blocks, the let block, the begin block, and the do block. We haven't encountered the do block yet, but those are the other three. I can't think of any other places immediately, at least not that you would have to use for this problem. So you have to do it for modules, which we'll talk about, where you store your code essentially, module and then end.
What's the difference between end and end with semicolon? In your examples, it's with the semicolon.
The semicolon, like with the other times we've used it, is essentially to suppress the output, right? Because every expression returns its value. If I just want to write a function and I don't want to see like the like f generic with one method sort of thing afterwards, then I can suppress the output with the semicolon. Otherwise, it just sort of means new line. Any other questions? Yeah.
Are there mediums that are preferred in Julia over others? Is the question of browse I hit submit?
Everything is kind of the same, and unlike a lot of languages like MATLAB and Python to some extent, depending on how you use it, loops in Julia are fast, like as fast as they might be in C for the most part. While loops are typically harder for compilers to figure out than for loops, but that's largely for the same reason that it's hard for us to figure out, right? Like while loops continue until some condition is met, right? And we can't predict when that happens. So if you have something that is statically sized, use a for loop. If it's not statically sized, you're stuck with a while loop and you live with that. But everything else, broadcasting and for loops are equivalent, right? So it's no faster to write a broadcasting expression than a for loop if you feel more comfortable writing for loops. That's fine.
Do you see how they did it though?
Anybody else? Yeah.
Is there a way to do this with the and or the ampersand formulation?
Sure, right. This is a ternary expression, so you could have kind of split up the ternary into the separate parts, right? It would be is even and div 2, and then you would have to check the condition again, essentially, right? Is even or for the second one. But yeah, you could do it that way. There's no reason to prefer the ternary over the separate ones. Most compilers will figure out that those are the same thing.
And is not equal to
Anybody else? Yeah.
But that's an even number. So it should run, which means I should have an integer.
Don't even check the elements or the variables. Doesn't like a specific measure. Default types of the variables.
That's an interesting question. So let's say I have n equals 1 here, right?
Right.
And what's the type of n? It is n64. So the reason that Julia is fast typically isn't that we can decorate these functions, with this syntax to say n is an int64, right? Because if I pass the callouts length, sorry, you can't see that at the bottom. If I pass the callouts length n, right? Julia starts, like I said before, Julia is a JIT compiler, or a better term is just ahead of time. So when I call this function, Julia will compile it given the arguments. And so it knows that this is an int64, and so it can tell all the way through the output, what those types are. So there's no reason to give a type, for instance, if the compiler can figure it out just fine. The big reason, I don't really know if I answered your question, you might have to repeat it for me.
In the function that you write, you didn't give any type to the end, it just call us length of n.
Hmm?
Yes. So if like I call this function on a string, what would it do?
So that's one of the things that is different between like Julia and like a super safety oriented language like Rust, right? Julia is typically used by scientists who largely care a little bit less about having super strict interfaces. If I were to call this on a string, we can see what happens, right? What I end up getting is the first thing that it encounters that it can't find how to do it, it will error, right? So this is a method error saying that it has no way to compare an integer as less than a string. This is potentially a good reason if you have something that's really expensive or really fragile to put the types on them. The other reason you might think is because it could improve the performance. And typically, so long as the inputs are known to Julia, you don't necessarily have to do this. We can use duck typing. The real reason, and which is the next section of the big sort of document, that we use types in Julia is for dispatch. If we have two different types and we know that there's a faster algorithm for this type and a faster algorithm for this type, we can write two separate algorithms. So that's the big reason that Julia uses overloading or dispatch. It's not really for behavior, right? We don't want multiplication to mean something different for a different type, right? Like it should mean the same thing for everybody. We use it for dispatch, and we'll talk about that. Is there anybody else on this problem? We're going to do a couple more of these bigger problems just to be sure that we've all understood how to write functions and do a little bit of the math and string stuff. All right. Next one is prime.
Let's see.
Note that I don't expect you to be super clever here.
Just put it all together. Okay.
The hint tells you pretty much exactly what you need to do. Someone did that suspiciously fast.
Is there an interrupt? Because I definitely wrote an infinite loop.
Control C.
That did not work.
I mean, you might have to kill it. It's a pretty dense
Yeah.
loop of computation. Julia doesn't have the best cancellation story these days. Alrighty. Should I try to slow it down a little bit more on the timer? Would that help everybody? Okay. Let me see if I can reload the question bank here. Collapse. This prime. All right, let me try to reload the questions here. course, I minimized that. Nope. Okay. Oh, well.
Zero one, not prime. If it's less than one, not. Split the equal number from 2 to the square root of n. One, if you get a remainder zero, it's not prime. Not easy. It's not prime.
Four. All right, I added a minute or two to each one. I don't want to spend too much longer than that. I will also publish the questions and the answers at some point before the end of the week. All right, let's see what this ends up looking like. Is buzz.
So yeah, it's returning that, it's ending that, but then it comes here and then returns straight. Oh yeah. Yeah, it needs to end there.
Question showing up for me.
Okay, does this function actually return? Actually work like this?
Are you able to sort of exit and rejoin?
Okay, so this will-
Yeah. Let me put the room command back up. Just reload Julia if you have to, but you should just be able to do this join quiz command right here. Yeah, sorry, I would try to reload it, but then it would reload it for everybody. If that happens to you, just try join quiz again. If it doesn't work, then let me know, and if enough people, and you can always quit Julia and rejoin with the same name or different name. Oh, I'm supposed to be doing this with you. My apologies. Okay, these guys. Sorry, I see my spam call there. Oops. In case you need to know the string function, it is just undercase string, undercase, lowercase string. Oops. What did I do?
Right?
Yeah.
Okay.
The system checks on one question specifically when It's just like. Also, I checked. It's also this parking.
Alrighty. What was tripping everybody up that time? Any questions, thoughts, concerns?
I think.
Yeah.
Why didn't you like this?
Either one of you.
That's a function. Defined. This is the problem. I always define this inside.
I module 15.
Yeah.
And the first like requirement was and, so why do you combine 5 and 3 to 15?
Because 5 times 3 is 15.
Oh, I thought it was like.
Well, right, if I is divisible by 15, it's divisible by 3 and 5. Yeah. You could just as easily have done I divisible by 3, double ampersand, I divisible by 5. They're the same thing. Yeah. It's just a different way to write it. Yeah.
It's the reason use the dollar sign. Like, is there a reason you have to like use string? When would you use string and when would you use the dollar sign?
So you could just interpolate into an empty string, right? You could do $sign I, but that's just kind of weird looking.
Oh, you need to put the quotation marks around.
Yeah. It needs to be the $sign means interpolation within double quotes. Yeah, I saw another hand up back there. Yeah.
Yeah, could you just remind me what is the semicolon for?
The semicolon is new line. This is just so that it fits more easily in the REPL. That is equivalent of me writing sort of this, right? And this. Yeah. Yeah, I'm sorry, that's confusing. I'll try to do that less, honestly. Like this is probably a more clear way to write it for people who haven't been reading a lot of Julia for a long time. Like that. Yeah. So semicolon does two jobs. It's a new line between expressions, and it suppresses printing the output of the previous expression. So that, which is only really useful in the REPL, right? If I want to type something and run it, but not print the result, then I can use the semicolon. But those are the two uses for it. Anybody else struggling with this one? All right, we'll do a few more and then we'll move on to the types and dispatch section. Once I can be sure that that page loads fully.
I think so.
It should print out.
All right.
It is an
Oh, there it is. Is palindrome.
So this is the prompt. I'm gonna assume know what a problem is.
So I'm going to throw up, rather than write things out, I'm going to throw up a few things with the
Is a problem drawn?
just the names of the functions that might be helpful. And then you should use the help REPL with the question mark to look at the docs. Okay. And these should make this a 2-line function. So the first one is lowercase. The second one is filter. The third one is letter. Pretty simple. And the next one is reverse. That should be all you need.
Yeah, for this, it's very helpful. And we need to do only this. Yeah, I mean, it can. Speed box.
If else needs ends.
No, but.
Did I not mention that one? My apologies.
This string as an input function to So the thing that is setting a string.
Oh, and others.
Just the price. There is some of these.
It just checks it because if guys added like double quotes or something, you don't want to count them like you don't count like the keyboard is point out. So you use three lowercase reverse and letter.
Yeah,
for example, if I want to check whether it's equal to
That's what here's.
I mean,
I think it is.
it's on Java. What we do it in Java?
Too many.
Okay, so I need to do, yeah.
Is that comma?
Yeah, no, it doesn't matter. I already submitted and it's wrong. It doesn't matter.
Oh, you already accepted this one.
Because lowercase takes the whole output.
Oh, you're
so-
But yeah, it was.
Oh, it should return something, right?
Yeah, it did.
Yes.
So what did it do?
All right.
This is Pluto.
So I do hear that it is difficult to type in the REPL, especially if you're not used to it. So if everybody could head to their in a separate tab in a new tab of their terminal in the same tab if they want to exit Julia, that's fine. I will. You can rejoin the room even if you exit Julia. So head to the QNumerics repo that you cloned or wherever you put the project.toml, and we're going to open VS Code there. You should be able to type code space period to open VS Code in that folder. This is the best way I know to be sure that you're all in the right place. There are other ways you can do open folder from within VS Code, but this is pretty easy. So the first thing that I want to be sure that everybody has is the Julia extension. So if you go to the extensions marketplace, you go over to Julia and it doesn't say that it's already installed, please go ahead and install it. Everybody have it installed already or just about? All right. So what I'm going to do is I'm going to do Control-Shift-P. I think that should be the same for everybody, but however you open your command palette in VS Code. And I'm going to search for Julia. And somewhere in there, there should be a start REPL. I know you just got out of the REPL. I promise it won't be that bad. So hit enter. And Julia will, the VS Code server will start to do its thing. If this is the first time you've used it in a while or used this version, it might have a bit of pre-compilation to do. The next thing I'm going to do is I'm just going to create a file and call it whatever you like, really, I guess. Scratch. And this is honestly the way that a lot of people do their development that isn't in sort of full-fledged packages. Take a look at packages, but if you're just doing sort of Scratch stuff like this, it's pretty easy. I can do, function foo, a, b. Of course, I'm going to pollute your namespace and use foo permanently now, but, well, kind of, you can replace it, I guess. And I'm going to return a plus b. I'm going to put my cursor up by foo. You can also select the whole function and hit Shift Enter. And then your foo is right here in your REPL, and I can call it on 1 and 2. I can do whatever I want with it. And I can continue to do that. I can even delete this, right? Like if I'm done with it, if I've typed and I don't want to see it again, I can delete it. Doesn't matter. It's already been put into the mind of the Julia REPL. We should be in the QNumerics environment or whatever environment you put that project.toml in. You should see Julia env QNumerics at the bottom. This should be true of most of the presenters this week that are using VS Code. You should see whatever project.toml folder down here. If you don't, then you're in the wrong place probably. You can change it. You can click on it and I can select different environments. I can select my 1.7 environment from, 6 years ago or whatever, or my 1.14 environment from next year.
But why not just do it?
Since we are in the right project, I can go back and I can do using quiz student, right? And I can do my whole thing again. So let me pull back up the joining tab, wherever I put it, somewhere around here, right here.
Excuse me,
Yeah.
could you remind me how to get into the project?
Can you say that one more time?
Like I have VS Code open and I did the start REPL, but I don't think I'm in the QNumerics project, even though I think I have that folder open.
Does your bottom, at the bottom, does it say Julia env anywhere? Okay,
Oh, it
thank you.
does. Yeah.
So this is right here. It's been word wrapped
Oh,
a little bit, but here's how you get back into the quiz from your new Julia REPL. So
Can you say again how your Julia environment is in QNumerics?
Hmm?
Can you say how you go to QNumerics?
How do you go to it? So there's a couple different ways. The first way is that you open VS Code in that folder. The second way is at the bottom here. You may not be able to see it very easily. I don't really know how to get it up further, but it should say Julia env and then something. If it doesn't say QNumeric, what does it say for you? Okay, so click on that. And what does it show you?
this is just.
Okay. Then you're probably not in the right folder, but you can pick a folder at the top there. So just pick the right folder wherever it is, and then you should be good to go. All right. What does what change?
Changing the environment, like freeze the packages in between.
Yeah. So environments, you have global environments where you might put, you shouldn't really put much because global environments can sometimes interfere with the other ones. So the things you might put in there are like benchmark tools, which is a tool for benchmarking things, or revise, which is something that VS Code does automatically. But I wouldn't put much else in there. And then when you go into a project specific one, then you can go haywire, you can put whatever you want and it won't interfere with any other environment. Yeah, not too dissimilar. They're essentially, it's just within a folder though. Whereas I believe virtual environments can sort of roam around. In Julia, it's largely a folder. You can activate it from everywhere, but it's a folder, right? And it's defined by that project.toml right here and this manifest.toml.
You find it?
All right.
Ah.
All right, I'm going to ask, let's see, what was the next one? Just one or two more, and then we will move on to the next part. Let's see. Who wants to do a Caesar cipher or who want, yeah,
Quick question, sorry.
Right.
With the REPL in the VS Code terminal, how do I get it to recognize scratch.jl again?
so if I'm in my environment and I have the REPL open, not a terminal, it has to be the VS Code REPL. It should just recognize whatever is in there, but it won't just run things willy-nilly. So I have to select something that I want to run. You know, I could select the whole file, right? But that I wouldn't recommend we do that today. But then just put your cursor next to foo, for instance, and press Shift Enter. You can also select all of foo or select, you know, a chunk of code anywhere, and it will run that.
Does it remember the variables we have defined?
This was used on the down the road, or like.
Yeah, so everything, yes. The fun part here with revised is, so, right, I have my scratch.jl foo currently adds two numbers together, right? I can modify this. I think this should work. It's been a while since I've used VS Code like this. And let's see. Do I have to do that? Maybe it's not working. Yeah. So I can change it to be multiplication and stuff like that just by editing the code and rerunning it. When we do move on to projects, where we have, you know, our own packages and stuff, which we might get to by the end of today, revise will not just like, you don't have to press Shift Enter. And it should be working. I'm not quite sure why. You can just type save and it will automatically update the things. It can be a bit finicky to figure out when it does that, but with packages, it almost always does. Did you figure out your issue?
So it says undefined array.
Okay, give me 1 second. Oops, wrong one. 6. No, 7, sorry.
Time for some cryptography.
Something more fun. Big Latin. Where'd you go?
Why don't I see the which one?
Big letter.
There is also another.
Yeah, no, that one I don't think.
Have you joined the, not really, okay, you can.
Like it's not in Scratch. So if I run Scratch jail, there's a reason.
Yeah, that's what I think.
Scratch. Yeah.
Really?
Yeah.
Do you have this?
Is this a case where y bounces a value? Okay,
And sometimes why?
and sometimes y.
Nobody.
Yeah.
So there are two ways of doing it.
Y
So you can
in
run
that
it
where it serves as the
without
bound.
being together.
Well, I have no idea.
Or you can do the same. Do this. You are searching this now.
No,
So if you don't know, you can treat strings a little bit like arrays sometimes. And so you can index into them. So to get the first letter, you can just do word one or whatever else your variable was.
Vowels are and sometimes what I would like that chunk that breaks is like.
Very fun.
Quick question. I don't know if this is relevant for your test cases, but what to do if a word has no vowel in the rules of Pig Latin?
Does Y count as a vowel in this case?
No, A-E-I-O-U. I believe you treat it as sort of the last case where you take the first letter, you stick it at the end and add AY.
So,
Here we go.
To no vowels? I think no vowels would just pass through actually.
Is this the right thing to use?
You use the hint that's and then switch. The word from I to N. They just use the hint.
oh, what was the
So find the bubble and then flip everything back into the axis. Yeah, but not cost plus the differences.
Yeah, I see.
Don't know. Is check one letter and it will directly check if each letter is a consonant or a vowel. If it's a consonant, then I take that letter, bend it, and remove that letter. But I also have to say that until you reach.
Say that again?
Yeah.
You can do either one. There's no difference. I think if you're doing pretty significant development work, it's always easier to open VS Code. If you are just experimenting, right, then I almost always just open the REPL. Yeah, in fact, if you have a complex function, you should probably be putting it in a package, right? And we'll talk about that. It's essentially the dependencies that you need. It has some structure. So like you'll have a module. And then once you have that, you can write things like tests and you can sort of easily export the function and stuff like that. Yeah.
Restart the regional.
You want a question? Probably not. Julia has never been the most very cool stickers, by the way. I imagine it seems like you might even have a key binding that is in the way. No, it's just nothing happened. Let's see. Yeah. Oh, well, that didn't work either. So,
Anyways, we can try doing this using this tool and then shifting this.
I hate how they do this.
Memory is not visible.
One sec, real quick. Let me just run. So did you install Julia? Julia is not on your path, is the problem. So how did you install Julia up? Or
It's just like last night from the website.
so you need to run one of these. It looks like probably. Well, let me see. Okay, so that's there.
I would try going back to
Julia syntax. What? Oh, something is messed up here. I'm just gonna do yield uninstall and reinstall, honestly.
If like you're not understand, it's not about.
I like how that made that number go
It's
up.
about the new stuff.
I think it exactly doubled.
Take the.
Yeah, I don't know. Yeah, I was definitely able to edit it like 2 months ago. I don't know what's happening.
Unfortunately, I would say.
Can we just like restart VS Code?
Well, one thing is I might.
Yeah, now you can.
Like this might be one of the things I can think of, but here in a sec, I have to send you maybe to Katie or.
Yeah, is it weird that nothing, like, I didn't have any problems until now?
I guess they're the same, so you should.
Yeah, a little bit.
First, so we don't.
You just had to, oh, you were in too big of a folder, I suspect. It will probably try and index all of the files. So if you open it in the workspace that is your entire home directory, then it will struggle under the load.
Appreciate it.
Okay, so I gotta move on. Okay, what's up? You have to do you have to use the package, so using quiz. Yeah, well, you should just be able to use those. Right?
I can just find it
One by one,
Or you can select the whole thing, but yeah. All right. Onwards and upwards. Let's see if the website has built.
Sir, in the answer, should you also add a?
I just didn't finish it. Okay, that has not finished yet. So not all of this is on the website yet because I believe it is still finishing its long build time. One second.
Yes.
I'll pull it up. Oh, wrong one. Of course. Yeah. So for now, we're just going to be operating off of this local build. I will tell you when the build is done so that you can go to this website, which is QNumerics.Raygun, which is my GitHub name.com, like that. But right now, the next part is not finished yet. It hasn't uploaded fully. So there will be little quiz segments. Let me reload the quiz to be the next set of them. All right. So I'm going to get rid of this and this. All right. So I've talked a lot about types. I've been hand-waving around them. I said everything in Julia has a type. Every value knows its type, its own type. Sometimes other people might be confused about the type, specifically the compiler. They'll never get it wrong, but they might be they might have sort of loose bounds on what they think the type is. But the type knows what it is, and so we can take a look at some of these types. Now I'm going to try and get rid of some of this stuff in VS Code so that it's a bit cleaner. So I don't love presenting in VS Code, but okay, so we're going to be using about. That should be in your environment. It's a nice way to check out some of the variables and types that we're looking at. So the first one we can look at is just a basic floating point number. We can see at the top that it's a float 64, and you can see this long subtyping chain. So what this says at the top here is that float 64 is a subtype of abstract float, is a subtype of real, is a subtype of number, is a subtype of any. That's kind of like this chain that goes down to the concrete type. So what we call it in the Julia world, when you have like an actual type that you can make. It's sort of the leaves of this tree that are formed by any at the root. And if you're really keen on how floating point numbers are represented in IEEE 754, I think, then you can sort of look at how that plays out if you want to type in different floating point numbers and use about to look at them. We can do about of 1. That's just the integer one. So on my machine and probably most of your machines, int, the default sort of integers are int 64. If you have an older machine, they might be int 32. Sort of if you just type 1, it'll end up being int 32, but I doubt anybody in here has that. And here the subtyping chain goes int 64, which is the concrete type, signed. integer, real, number, and any. So we can see it's part of the same set of branches, but it branches off after the real numbers from the floating points. We can look at the Booleans. So if I do true, hope I'm not getting a parking ticket.
No, you have to say using.
Bool is a subtype of real, a subtype of integer, but it's just the integers 0 and 1, right? It's that is the domain for bools. And the representation is pretty simple. It might be surprising to you that it is that large of a number. It takes up a whole byte. Most computers do not accept bits. So you won't typically be dealing with bits. You will almost always be dealing with bytes. You just load memory in terms of bytes or even larger than that typically. So we represent true and false, but we use a whole byte to do that. And that's true of every programming language under the sun, except for a few special cases. Yeah.
Sorry, I think I missed this. Why did you need to write using about?
Because this about function that we're using is from the package about. Sorry, I should have been specific.
Oh, okay.
Yeah, this is not a built-in feature of Julia. This is from the nice package about, written by Timothy. He's one of the people who's working very hard. He probably works the hardest on making Julia prettier. And that's why about is sort of kind of nice to look at, a lot of colors. Let's see. We can do about of this tuple here. So what does this end up looking like? So the tuple has a memory footprint of 32 bytes. That sounds about right. We have two integers, the first two, and they take up 8 bytes each. The next two are pointers. So the string is a pointer internally to somewhere else, and that's where we store ASCII and the angry emoji, angry face emoji. We can see that tuple of int64 string is a subtype of any. But let's see. I'm going to do type of. So let's call this T. I don't think you can see this because it's too far at the bottom of the screen. So I'll try to clear it. I'm just going to clear it all the way up here. So that's the type of my tuple. We might write another type, tuple of, oh my God, stay, of integer. Why won't you stay? What the heck?
Just revealing.
String. We're going to call that U. And that is just the type U, right? We have this type, but we don't have an actual value here. This is the value that represents the type tuple of an integer, not a specific int, right? Not int64. This would be an abstract integer. And then 2 strings, or 2 integers, 2 strings. And even though I told you earlier that the supertype of that tuple T was any, you can find other supertypes in between. So in this case, we have tuple, integer, string is a supertype of our tuple that we wrote earlier. Now, what happens if we write vector int64, right? This is the type of a vector of int64. Pretty simple. You can see it's an alias for the one-dimensional array of int64. We'll talk more about parameters a bit later. And right now, these are parameters that we're doing, right? The tuple U is parameterized by integer, string, right? This is, you can kind of think of this as generics, right? Or something similar to that. So we might call this type A for that vector. And then we might have vector integer. Right, and this is the vector that can store any subtypes of integer. So if I have an int32 and an int32 and an int64, I can store all of those in this vector. They'll probably be pointers. They won't be packed together in sort of one contiguous array, and that's why we really like homogeneous vectors. We don't care for tuples because they sort of store inline pretty much no matter what. They're kind of their own unique data type. And the other thing that makes them unique is that they're contravariant. Convariant? Did I just miss Katie? Is it contravariant or covariant? It's covariant, isn't it? Tuples. Yeah. So tuples are covariant, and all of the other types do not behave this way. So you saw that this this tuple here was a subtype of this one, right? These two integers matched with these two integers. And so int64 is a subtype of integer, int64 is a subtype of integer. And then because this is a tuple, it's special, it's covariant. And the reason for that is because, like I mentioned, you should kind of think of tuples as the signatures of functions, right? You might think of this as the representative of a function that takes two int64 and two strings. You might think of this as the function that takes two arbitrary integers, whatever ones they might be, booleans, int64 and 32, and two strings. Yep.
It never explained to me what covariant and contravariant means in the context of software. If you could elaborate a bit on that.
Yeah, so I don't have the biblical definition in front of me. Essentially, in this case, I don't think contravariant, that was the wrong word. I think the rest of the types in Julia are invariant. So covariant in this case means that for tuples, because they represent the signatures of functions in some sense, that their subtyping relationship varies with the subtyping relationship of their members, right? So if their members are all subtypes of each other, disjointly, right? Like the first one is a subtype of the first one of the other tuple, right? Then those tuples are subtype, there's a subtyping relationship there. With other types in Julia, this is not the case. And the reason for that is a little bit obvious if you know much about computers. And it's also just sort of the way things have to be for performance reasons. And the reason is that, like, the way that we store an int64 in a vector is sort of a homogeneous thing. We know how to store it. The way we store a vector of integers is as a bunch of pointers. You also don't really have this issue with tuples because tuples always have their concrete type, right? So you can kind of think of this as an abstract tuple right here. This isn't super important to get right coherently right now, but we'll see more and more as we write out functions with types in their names. You'll see why this sort of makes sense, why tuples behave this way and why nothing else behaves this way.
Or like, is the like, what I'm wondering if this is
if you want, once the website is loaded, let's see if it's done. No. You can take a look at the about for a ton of other different types, right? The about for a vector, the about for, a vector of arbitrary values. So here, this is a vector of any. And so it is a pointer to a list of pointers internally, right? You don't have to think about pointers in Julia, but, when you see something like a vector of any, you should know that it's not homogeneous. It's not, one value after another. It's your computer has to chase down and find the value and then find the next value. And that's really problematic for performance reasons. All right. So we've seen a few concrete types. It's time to look at most of the concrete types available to us. So I'm going to do using abstract trees and using interactive utils. You can do that in one line with just a comma between them. And abstract trees is, as it sounds, it's a package about abstract trees. And one of the nice things is that it makes it really easy to print things that are shaped like trees. So if I have a type T, right? So T here is the variable. It has, it's the argument. It has the type, so it will be, int 64 or vector int 64, right? It won't be a value of those things. It will be the actual type itself. And then we can use the subtypes function to find the children. That lets us create a tree, right? We can use abstract trees to make this nice and concrete instead of, within the compiler. So I'm going to print tree, and we're going to start with just number, right? So number is our super type for all numbers in Julia. And I'm going to print the tree, and you can see we have all these types. So the direct subtypes of number are multiplicative inverse, complex, and real. We've seen a lot of things with real. So the next thing below real is an abstract float. And in there we have float 16, float 32, float 64. And these leaves that you see are concrete types. When you have a value, it has one of these concrete types, one of these leaves. It never has the type abstract float, right? You can have a storage location that is ready to store abstract floats because it could store any of these types. But you can't have an abstract float, right? You can't make something that isn't a leaf of this tree. Then you have abstract irrationals for the irrational numbers, like 1 double backslash 3. That's a rational number, actually. Geez. At the bottom here. And then the integers, which have, bool, and then the signed subtypes of the integers, which are, int 32 and 64 and 128, and the unsigned integers, uint 128. So that's the tree for number. We can ask, what's the super type of number? And it's any. So we could try this. I don't really know what's going to happen, honestly. That wasn't what I wanted to type. This was. Let me print trees.
Oh my God.
So you can see here's all the types in Julia right now. Well, in my install. And this will keep going for a while. You can see all these type ofs, right? You saw a lot of those there. That's all your functions. So what's happening here is that every function is also a subtype of any, right? And so there's tens of thousands of those probably. The vast majority of those types you will never see. SSA value, unless you become a compiler engineer, you're never going to see that. Or interpreter, frame data, yeah. But this is a lot of things. My REPL cut off there. Not very far down the list, honestly. Let's see. So you've seen the type tree. Everything is part of the same type tree. Everything is a subtype of any. Maybe not in 1.15, but that's completely arcane knowledge. For our purposes, any is the be-all, end-all. There is the sort of mirror of any is bottom, the bottom of the type lattice. If you ever see that in your error messages, you have gone deeply wrong, and something bad has happened to you. And I recommend you angrily email one of our compiler engineers or something. So there are operations you can do with these types. So we can see this is the subtyping relationship. Int 64 is a subtype of integer. That's true. Float 64 is a subtype of integer. That's false. And then we can do the reverse. Number is a supertype of float 64. That is true. And of course, trivially, any is a subtype or is a supertype of float 64. You almost never see this symbol right here, the supertype operator. You almost always deal with, like 99.99% of the time, you're dealing with the subtype operator, right? Because you're trying to specify a more specific function. All right, it looks like maybe there is a question lined up since I managed to mark the questions this time.
Yeah.
I don't know what that looks like. Oh, here's my thing. Which of these subtype expressions evaluates to true?
I don't know for.
Well, I guess if everybody can see what everybody's picking, it's kind of
But I don't know about for.
defeats the purpose a little bit.
Yeah, so what is the truth? Maybe I can just check.
So how do we relate values to types? Typically in your functions, you shouldn't do this very much, right? You want your values and you want your types to live in the signature of the function, right? And we'll see what that looks like. But we can check if a value is an integer, right? 1 is an integer. Is 1.0? No. We can check to see if 1.1 and 2.0 is a tuple. And I put a space, and so that's invalid, but yes, it is a tuple.
Which one is false?
So I think there is another question on the ISA, and I'm going to this time leave the thing.
One question.
Yeah.
So I noticed that super type of int64 doesn't have complex. How are complex numbers stored in Julia again?
If we look at that print tree of not any but number again, we can see that complexes are a subtype of number.
Okay, right. So real and complex are stored as two separate kinds of branches. Then, as you can see.
Yeah, they're different branches of the tree, right? Because real and complex are disjoint, right? Or I guess. Yeah, for our purposes, they're disjoint. We aren't dealing with a situation where we want to treat one as like a subspace of the other or something like that, right? Because typically when you want to ask about a values type, you don't really want to know, is this a subspace, right? You can ask that in other ways, but it's just not really a valuable thing to do from, like I said, implementing algorithms, right? We really only want to use dispatch in Julia, not for correctness, but for implementing something faster for a certain number type than the other one. And in that case, we want to keep complex separate. Complex is a little weird in that it doesn't have this sort of deeply nested hierarchy, right? And that's because complex is parametric. So, you represent a complex number as two real numbers essentially. And so you only really need one complex number because it's parametric on the other two.
So I can specify the type of the real numbers that go into the complex?
You can. So it's parametric over them. So if I look at complex, then you can see it has this this is its format. I don't know what this I don't like this weird highlighting thing. Complex contains a T, which is a subtype of real. And it actually contains two T's because they have to be of the same size. And so what happens is you could put bool in there, right? Complex of bool. And that's fine. You could put complex, and most people though put complex float 64. Yeah. Or 32 or 16 or.
And that would mean that both numbers that go into the complex are of float 64 type.
Yeah, so here's how complex is typed out. We'll see more how to implement structs. I don't mean to sort of jump the gun here, but just so we can answer the question, maybe keep some curiosity going. This is subtype of real. This is subtype of number. And then this would be real T. So the real component has type T. And the imaginary component has type T. And then you end, and that's the complex struct. Yeah.
Behind the curtains, is there something like C++ template metaprogramming or?
To some extent. The joke at MIT is that Julia is what would happen if you shove the templates all the way down. So what happens is that each, and we can look at how this is fully compiled if we'd like later when we talk more about performance a bit more rigorously. Essentially, when you call a function in Julia, functions and data are completely separate, unlike C++, right? There's no like virtual functions and like member functions and stuff like that. You have functions and you have structs. They're completely separate. When you call a function, right, whatever it is, and you give it the data, Julia compiles that function given its types, essentially in the same way that the template metaprogramming happens, right? You can kind of imagine if I were to give the addition function two complex numbers, it could be like the template has two slots, right? And then it fills out the rest of it. And so internally, that's kind of what it is. It's almost like a more ergonomic way of writing a C++ templates. So yeah. All right. Ooh. So I hid the answer this time, and we didn't do so well. Let's see, what was this? Oops. Wait, what? Those numbers don't add up together, regardless. All right. So we showed him a second ago how to do supertype and subtype. So supertype of int64 is signed. Subtype of int64 is, there's no subtype, it's a leaf. Supertypes of int64 is the, why is, I don't understand. Stop disappearing, please. I'm begging you. That's the full chain all the way up the graph. We can do subtypes of integer. And this is the direct subtypes. It's not the chain down, right? It's just bool, signed and unsigned. We can do the same thing for abstract floats, for instance. Abstract float. And you can see we have big float, B float 16 if you really are into machine learning, float 16, 32, and 64. I'll skip this question. It doesn't seem all that difficult. All right. So I mentioned that there were abstract types, right? Those are the branches of the tree. And there are concrete types. Those are the leaves of the tree. Is an abstract type number is true? Is an abstract type of int64 is false, right? Because it's a leaf. Give the same thing for is concrete type. You shouldn't typically be asking this, except maybe at the REPL, right? Within a function, you should know what you have. You don't want to be checking these things dynamically, right? Within a function. One other thing you might want to say is, how do I say that I want this function to take either a string or a matrix? I don't know why you would want that, but you can multiply both of them, right? Not together, but like two strings and two matrices. But there's no easy way to talk about that within the type tree. So you can do what we call a union. So a union of int and float 64. One is a subtype of that. High is a union, is not a union of int and float 64, but it is of abstract string, right? And if we take a union of int and float 64, we know that that's a subtype of real because both of those are branches or leaves that emanate from real. You also have the nice property that union of int just gives you, well, int is an abbreviation for int64 here. So, unions collapse down duplicates. You can get away with using unions a bit, but if you're using them too much, you should strongly reconsider sort of how you've laid out your type tree and type signatures. Julia's linear algebra library has some of the most horrific unions you've ever seen in your entire life. Let me see if I can linear algebra. Is it strided? Strided. Maybe edge. So there's a union that you don't really want to see in your daily life. You saw that in an error message. I wish you well. Although error messages are pretty well highlighted these days that will tell you what's going wrong. I don't mean to scare you, but mistakes were made along the way as Julia was built. And sort of some of the unions in linear algebra are one of them. The big problem with unions is that you can't extend them. Once you've declared a union, it's locked, it's done, it's sealed. You can ask somebody to add to the owner of the union to add more. But that can potentially break other things, right? Because you're changing the membership of this thing that we're using for dispatch.
Can you say again what is a union?
A union, so a union is kind of like a grouping of types that you can't say have a relationship on the tree. So we have this tree of types, right? And we can say, oh, I want a real or something. But it's not very easy to say, oh, I want either a string or a matrix. And so a union gives you a way to say, I want one of, but not all of these, just one of this set of things that is sort of arbitrary. You get to decide. And it's easy to abuse, but it's super powerful for the same reason.
That's the question.
Hmm?
I just didn't understand how high is a union of int and float. I mean, if it was just a char, I can understand. We can represent chars as integers, but how to represent a string as an integer? So it's a union of float 64 and int.
How to represent a union, like which union? So when you have a field that is a union, for instance, in a struct, it has the type union. Typically, that means it will be stored as a pointer, not as it won't convert to one of the other types in there. Can you repeat the question though? I'm not sure.
My question is, for example, 1 is a union of the integer and float 64. I can relate the number 1 with these types. But how can we relate high with the integer? I mean, if it was a char, we can relate a char with integer, but normally high is a string, an array of chars. So how can we relate them to integers or floats?
An array of char?
For example, that high.
I'm not hearing that word. Sorry, I'm actually pretty hard of hearing.
Normally in C or C++, a char is an integer, right?
Yeah.
Like we can represent it using 2 to the power of 7 or 8. So I can relate it with the union of char and integer, right? In Julia, or example, union of integer or char, float or char. How can we relate the high? It's a word where it's a string, so I didn't get the relationship between the high and integer and float 64.
Oh, up here.
Yeah, up there.
Yeah, sorry. So this is high is a union of int and abstract string.
Yeah, abstract string. I'm okay with that, but what about integer?
So a union is you can think of a union as similar to union types in other languages, right? So a union is it's one of these things, but it's not all of them. Right? There's no relationship between them except that you sort of group them together and you say, when I say high is a, I'm saying high is an instance of one of these things, but not all of them, right? So there's no relationship here implied necessarily between high and int.
Okay.
It's just between high and abstract string. But we've grouped them together because I might want to take, I might want to have a function that can take a string or an integer. But when I get that string in my function, it is a string, like not abstract string, not int, it is string, right? So as I mentioned before, types always know what they are. So there's no relationship here between int and high. It's between the whole group union here and high. Does that make sense?
Yes, so can we say that the high is stored as a pointer in the memory, and we can represent any place in memory by integer? So that's why in that union integer makes sense, or not related to that one?
They're orthogonal there, right? The representation of the string high there is largely up to the Julia compiler. So it has nothing to do with, right? I could do high is a, you know, union matrix matrix of yeah, sure, float 64 and abstract string, right? It doesn't matter what I put in that other type. I could put something that's completely meaningless, right? Like it's just I've grouped these two types together, and the is a relationship is saying high is a member of one of these types, but it doesn't matter which one. If I were to put this union on like the field of a struct, then that does mean probably that high is being stored as a pointer, and there is a tag that says what it is. But you know, strings are always stored as pointers in Julia, unless they're interned, which does happen occasionally for small strings. But well, I guess that's a pointer anyway, isn't it? Intern strings. Yeah. So the string will almost always be a pointer, and so will the matrix, because a matrix is a mutable type, as we'll talk about in just a minute. All right. So we've looked a little bit at unions. We've looked a little bit at supertype and subtype. If you feel like you're getting bogged down in the details, come talk with me. We can whiteboard. We can do whatever it takes to sort of help figure out how multiple dispatch and the type system works. The next thing we want to look at is maybe how structures work. So here are the field names of a complex whose parameter is whose element type is float 64. Those are the same field names for complex without any parameters, but you know, for sake of concreteness here. And then we can also look at, so that's real and imaginary are the two field names. The field types are float 64, float 64. And we can also look up the specific field type by using the symbol for real or imaginary. If I look at something like this, you can see that I don't have any, right? Because I restricted, as I typed, and you know, as typed in Julia's standard library, the field types of complex are restricted to be real. You know, you can't have a complex of a complex, or you know, some of the other options. So we've been looking a lot at types. I want to remind you to think as hard as you can that there are two things in Julia, functions and types. Right, functions do have a type, but otherwise they're completely separate things. They're orthogonal. You know, types don't have their own member functions, for instance, like they do in Python or C++. They are free floating. But we can still ask some questions like, what are the methods that contain unsigned? And we can see that the methods that explicitly contain unsigned, there's about 37 of them. But I think you should probably realize that this is not the full set of methods that are applicable to unsigned, because all day today we've been writing methods, you know, or functions without types in the signature, right? And so any one of those, provided they fulfill the interface needed by unsigned, can potentially be one of these methods. They just aren't written that way, right? So one of the weird things about Julia is that you can't really enumerate all of the functions that will apply to your types. That's a lot different than C++, where you might do, you know, foo dot, and you see all of the methods that you can apply to your type. And this can be a bit of a problem, right? If you're looking for a function and you know it applies to your type, but it's duck typed or it has, instead of having type unsigned, it has type integer, you won't know that it's available necessarily. So documentation is really key in the Julia world. I'm going to skip over is-bits types mostly, but if you're familiar with plain old data, POD types, from other languages, is-bits types means that it's essentially all of the type is in one place. It's all made of bits, there's no pointers. That's really important if you want to store everything in one place, right? If you don't want a bunch of pointers off to nowhere. All right, now we can start to make our own types. The first one that most people make in Julia is the point type. So float 64, float 64. And now we have a point. You can imagine this looks a lot like the complex number. And I can make a point. So constructors, just like their types are typically capitalized. 2.0. What is with this weird like folding thing going on? And now I have a point P. I can access the fields of P with p.x, p.y, and I can look at the type of P. Linked. Ignore the weird mess over here with Franklin. Because we just wrote struct, point is immutable. So if I try to do p.x equals 10, I will get an error. Set field, immutable struct of type point cannot be changed. Immutable structs are great for data, right? If you have something that it looks like a number, if you have something that is always the same size, it should probably be an immutable struct. If you can find a way to make it immutable and you don't care about static identity so much, then or memory-based identity, then you should make it immutable. What I mean by memory-based identity, to clarify, is if I wanted there to be 2 points with the same data, but were not identical, right? I might have 2 John Smiths, and they're different people, but if they're an immutable struct, they're the same thing, right? They're just like the number 1 and the number 1. But a mutable struct has identity based on its memory location. So I could create 2 John Smith structs if I put 2, X be string and Y a string. That's an important distinction sometimes to make. All right. There is a little quiz. Hopefully everybody gets through it very quick because it's very simple. Nope, next one. Yep. All right, a lot of people have answered now. I'm going to move along. We can make mutable structs, like I just mentioned. Here's a counter.
Okay.
Mutable structs are largely distinguished by having the ability to mutate their fields. That's the semantic difference. And like I said, there is a bit of an identity difference, right? If I create 2 of these structs, counter 1, C equals counter 1. Oops, I forgot to press enter. And D equals counter 1, right? If those were numbers, those would be identical. Let me move this up here. But because they are mutable structs, C is not identical to D. They are, however, as I mentioned earlier. Oh, I guess that's not true.
I don't know. C++.
Can you do that? Nope. Okay. There are versions of identity. Sometimes you can overload them to be where you can ask if they're equal on their sort of fields, and then unequal if you compare exact identity. But we can now mutate this struct, right? So c.n plus equals 1. And so we have rebound c.n to be 2 now. We can do it again. We'll get, the same result as adding again.
Yeah, yeah.
And ask the next question about identity.
She said there'd be 2 Smiths. Maybe something that might be. Maybe constructor that as well.
Seems to be too.
Looks like most people are getting B. It is that mutable structs use identity. So egal is the name of that 3 equal signs in a row, the egal function or operator. All right. Parametric structs is the next thing. So if you've been wondering how to create your own vector T or, complex number, this is how you do it. Struct of a pair with element type T, and we have X of T and Y of T. So what happens if we do pair 2, 1, 2? We get a pair 2 of N64. If we try to do this, you'll get a method error because both of those T's are the same T and they have to match. You can also do something like this. If you think for some reason that you want the element type to be different, for instance, we might make it real. This is an abstract type, right? The fields of a struct can be an abstract type, but the things that we put in it, we'll still remember what they are, right? So this pair 2 of real will contain any of the real types. Of course, it's a struct, so now that we've bound it, you can't change the values. But you could put, that like that, because it expects that it's any subtype in either of those places. Why is that not exactly the same? I believe that is. Oh, no, it isn't. So the next thing we can do is constrain our types, just like we did.
Quick question.
Yeah.
When you define something like this with with the T, if I don't specify the T, so if I were to just say pair 2 bracket 1 comma 2, because 1 and 2 implicitly have the same type of int, does it work?
Yeah. It will typically do its best to corral everything into the right place, but it won't sort of convert one. It typically won't like convert one in a different way than the other, right? It expects that you're getting T in both places.
And does Julia then take like the highest level that fits, or so like if it was just 1 and 2, both int and unsigned might work? Which one was Julia?
There's a set system in Julia called promotion. It's a pretty interesting conversation to have, but it's a pretty in-depth topic. It's a pretty complicated bit of code. I don't know the promotion rules. I believe that if you had an N64 and a UNT64, I believe that it would promote the UNT64 to the N64 unless there was an overflow, in which case it would error. Okay. Because the domain is not wider, but has more information, I suppose. So for number pair, we have constrained T to be a number. So number pair cannot contain, for instance, a string and a string. But it can contain, 1 and 3. And that fits just fine. So we can ask a quick question about dispatching, where you can define your own parametric struct. Where did it go? My scoreboard. There it is. We'll wait until about half of the people connected are done.
Yeah.
Why did you put him? Wait, because it holds up here and then.
How many have these are here? What did you do? No, for why I didn't submit it for you. This is and then you have to take these and
All right, that's about half the people. What we're tripping everybody up on this one? I'll show the answer here in a second, but for now I can just say that the answer looked something like
take this piece of box.
that was the struct. I imagine some of you just put the struct in, which is fine.
But that didn't take.
Hmm?
It didn't take.
Yeah, I know. I'm saying like if you got to this part, I'm not really concerned about it. I need to find a better way to do sort of the checking. The problem is I just don't want to run your code on my computer. So I need to figure out a way to do that better on your computer. Or just write the questions better, honestly. All right, so long as you got it something like this, and then I think what it wanted was, B equals box of 42 or something, box of 42 or something like that. And then to just return B. Alrighty. Next, we'll take a look at defining our own abstract type. We can just write abstract type animal. It looks a little bit different than all of the other declarations of things in Julia. It's pretty rare that you have two keywords next to each other. You can't write type Julia or type animal, sorry. This is largely a layover from back when structs were called types. So I can create two singleton types, subtypes of, oh, these are missing the ends here. No, it worked. Okay. So you remember when I talked about the nothing type earlier, right? It was a singleton type, sort of nothing is a nothing. This is sort of the same way. So we have a dog, and we just have the one, that's the type dog, and then we just have dog, and that's the one dog. There's really just the one. So I can make another one, and it's the same guy. So, might as well just make a constant, const dog equals dog, right? Oh, it already had a name, sorry. We can do const cat equals cat, I guess. And so singleton types are pretty useful when, for instance, you might want to represent something like nothing or missing. Those are two types in Julia. So missing is kind of the data science equivalent of nothing, right? You might be missing a value in some data frame. And that's a singleton type, just the same way nothing is, and just the same way cat and dog are. We can ask questions about these guys. So, a cat, is there something missing? Oh my, this copying really is bad. These weren't intended to be singleton types. Unfortunately, you cannot erase types just like you cannot erase functions. And more to the point, you can't even redefine types. So in this case, they were supposed to take a name, unfortunately, instead of just having the one cat and the one dog. I don't know why this copy button does not work very well. I'll have to keep an eye out for that. Let's see. You know what? Let me exit this. And I can do this properly. So name string end, and then name string end. And then I have my creatures back. Why can't I scroll up? Oh, because I did it all at once. Let's see. So Rex says woof. Mia makes a sound. You'll notice that let me see here. The speak for animal will apply to both Mia and Rex until the second method was created. When I say method, this is what I mean. Speak is the function, right? It is the overall idea of speaking, I guess. And tied to it are two methods: speak for animal, all animals, and speak for just the dogs. So a method is kind of like a subtype of a function in some sense. A bare function, you can actually just type function foo. A generic function with zero methods is kind of, in some sense, similar to the any type, right? And then you can make subtypes of this function, which are the methods of that function. So let's see, there's one question which I would like everybody to do about dispatch here. So I define an abstract type vehicle. That's not too different from how I did animal, just a different name. And then here, remember, you should do these outside of the quiz REPL so that you can then return C equals car4, right? That's how you get the correct answer here. You don't want to return just the type or, just the abstract type vehicle. Okay. Sorry.
No, no, it's, I did the whole thing. I sent in C. Thinking that might be.
When I create an abstract type, can I still say that the abstract type needs to be some type of another
I
existing
also did just C.
type?
Yes. Subtyping construct, right? It'd be abstract type. Number, subtype symbol, right?
Oh, yeah, you're not in the
Caret,
question mode.
colon, and then number or whatever, and then end.
If I do that, then
Wait, do you have to
do
be in it?
functions defined on the supertype carry on to the
But I was
subtype that
saying
I've
maybe
just done?
you were
Because
in-
something like a vehicle, for example,
No.
I assume you can't do any addition, you can't do any operations on it that you haven't defined, right? Like addition isn't
Typically,
good.
the operations on the abstract types are defined by operations that end up being on the property. You cannot add sort of things without having some of the primitive operations for that abstract type defined. Right, so typically for number, that's addition. It's also typically for number promotion, right? So honestly, I think you may be able to get away with just defining promotion for certain number types. But you definitely have to define promotion. If your number type can only be added with itself, then you don't need to, right? Then you would just define plus and that kind of stuff.
So you have to run it here, but I don't know.
Oh, they are same stuff.
One of the best ways to illustrate this,
I have no idea how to
we
change.
might see in the next 20 minutes or so, is the abstract array interface.
Oh, just do it.
So for abstract arrays, right, you might define an abstract matrix. You don't immediately gain multiplication because you have to define size and how to index. Once you've done that, you do gain multiplication. And the method technically would apply to you, but you would get a method error once it tried size.
Okay.
Right, like if you try to do a matrix multiplication and your matrix didn't define size, it would throw a method error when it tried to use size. Right? When it tried to compile in size. All right.
Inheritance real fast before we move on. So maybe this is just coming from the fact that I like object-oriented languages and I haven't adjusted to Julia yet.
Thanks a bit, yeah.
But I will sometimes be writing something in Julia and I think it would be really nice if this abstract type could have some fields in it. For instance, like maybe every animal has a name. And I want to give like animal name string, but I can't do that. I have to give it to every like child of animal. Oh.
You're talking about issue 4935. One of the older issues that is still opened by the creator of the language himself, and unanswered for 13 years. Generally speaking, I think the Julia community prefers composition over inheritance, which is a very hand-wavy way to answer your question, right? This is often. which is a very hand wavy way to answer your question, right? Without a specific example. But yeah, I think in general, the Julia world prefers that you sort of inherit some behavior, but nothing else.
Okay.
And the reasons for that are varied, but the biggest one is that Julia's sort of key idea outside of multiple dispatch and, like outside of the technical stuff is that anybody can, this is called the expression problem, is that I can have two other friends and one of them creates a set of functions or a function, and the other one creates a type. And I can create, without talking to them, I can create a function that works on my friend's type and a type that works on the other friend's function, right? And the more that we encode sort of structure into inheritance, the less that's possible, right? Like if these fields were mandatory, it might not be possible, for instance, to represent like a vector of all ones, right, with just a constant, right? Because if the definition for vector included like a pointer to memory or something, right, I couldn't just have this constant. So the idea, I think, is that we maintain a lot of flexibility by avoiding having fields as part of the definition. It is perfectly possible for you to document that, each type in this subtree, in this inheritance tree that I own, must have this field. For instance, maybe I have a lot of functions that access that field directly, right? So a lot of Julia's interfaces, which don't really exist, they're entirely documentary in nature. And that does lead to flexibility. It also leads to people saying, why doesn't this work after they've like walked very far off the beaten path, right? So yeah, there are a lot of these things, these issues are like that are very old in Julia around extending the type system. But I think the general idea in the Julia world is we've gotten reasonably far without much extensions beyond a single inheritance, sort of. Yeah.
Okay. So how then would you recommend, let's say I have 10 child types of an abstract type, and they each need to have a set of several fields that's like duplicated across. If I don't want to write the same bit of code for each child's type, then
If it's not very many types, I would say suck it up. If it's a lot of types, then you could use a macro that just inserts them, right? It would be like at my fields or something like that. That's one thing that macros are good at, making code that's repetitive easy. The other thing you can do is you can, in Julia packages and in the REPL, you can evaluate code in a loop. So you might have a loop that loops over the names of your types. And if they all have the same set of fields or something, right, you could just loop over them and write them like that. Sort of essentially doing string interpolation.
thank you.
Yeah. Oops. I'm going to quickly glaze over constructors. I think they're important, but we have other places to be. I lied a little bit when I said that there were no functions that were attached to, no sort of member functions. The one case of that is constructors. Constructors are actually not really member functions like you would think of in other languages. It's just a function that dispatches on the type T, and the type T is, the T is the thing that you're constructing. So, I don't know, I don't want to show all that. There's two types of constructors. There's outer constructors, which are just the function with the name that is the same as the type. They can appear anywhere. I can make them in a different package, right? If you make the if you write the struct Fahrenheit, I can, in my own package somewhere else, also create a constructor for Fahrenheit that creates your own type, right? The one thing that you cannot extend is inner constructors. Inner constructors are how you might enforce invariants within your code. So inner constructors are only allowed to be created within the struct definition, right? So if I'm in the REPL, I write struct positive int. It has n as a field and it's an integer. And then I write the function right here in line. positive int. And it doesn't have to take an int for here, right? It could take something else and transform it into something I can put into my type. But then within this constructor, I can enforce the invariant that this is 0 or I throw an error. Blah. I don't want to type all that. Within inner constructors, you have access to the special new function. Essentially, the new function is just you put the variables in order into the new function and you get out your type. So in this case, I would just put n into the new function. And for some reason, I forgot a parentheses. And then if I try to do positive int, and I do -3, in this case, I'll get this error that very kindly says ASDF. Inner constructors are really only when you really need them. I think it's for things like that where positive int must indeed maintain the contract that it is a positive int, even if someone else writes a constructor for your type. Otherwise, I wouldn't use them too much. The other way that you can use new is with the parametric new. So, if you have parameters of your type and you need to be specific, you can write new curly brace the parameters that you need to put in there. All right, there is the reverse. Nope, next one. Wait, what? Did I skip a few? Oh, I went way too far. You don't have to do that. Ignore that. Ask. Let's see. It was supposed to be inner CTOR. It's supposed to be 13. There we go. So you want to define a struct pos int. Wait, is that exactly the same? It is. I'm going to scroll down so you can't see that anymore. So it's pretty much exactly the same thing as we just did. Just remember to define it in your normal REPL and then submit it in the quiz REPL. What's up?
Yeah, so I think there are some things like, for example, like when you were doing this point thing with that, I mean, this was like a little while back. So for this past one, I accidentally typed in, like I was just typing in everything. And then like I didn't, I wasn't even thinking that, and then when I hit enter, like you started the quiz before, so I already submitted.
That's fine. Yeah.
Yeah, anyway, I thought that would be a good opportunity, like, okay, so I do like point, like for example, point, and then I run this in my terminal. So then, I guess something like this, and then this has been like this whole second section. I haven't really been able to resolve that. I think I should be able to like do it here and then run like,
Yeah. Oh, it's because this is your Julia REPL. This is a separate terminal that you've also just opened Julia in. You need to be sure when you're trying to do this like control or shift enter thing that you're in the Julia REPL that VS Code opened.
Okay.
Yep.
I think so.
It's a program. Let's see. Okay.
It has to be inside the functions. It's inside the function. Yeah, it's not inside the function, it's outside the function. No, it's not. Yeah, but it should be inside the function. Should be inside the function. Yes, it's out. Also, you get some. Yeah, I'll try it. Yeah. Oh,
All right. About half the people have answered. Let's see, does any of the answers show anything interesting? Looks like it was nothing. Again, any of these examples, if you feel like you struggled with it, you can come back to me. I will send out the URL in case you haven't already gotten it for the site. I think it's pretty much done building. Yeah, it's been done for a while. All right, I kind of want to show you what's happening in a less textual way than we see, in the REPL or in the IDE. It's kind of hard to get a grip on what's going on if you don't really see it. So we're going to play rock, paper, scissors. I have an abstract type shape. There's no real strong reason for me to have an abstract type here. I don't do a ton with it, I don't think. Oh, I do something with it down here. And then I create rock, paper, and scissors. And I create a couple functions. So this play here, this is the syntax for how you write a function on, how you dispatch on types. So when somebody supplies arguments to this function, they're going to be supplying types, not values, right? It's not going to be the value that is the singleton paper. It's going to be the type paper. So you write : type paper. If you needed to refer to paper for some reason, you might write : type T, and then you might have this is the way that you refer to parameters is with this where syntax, in case you see that coming up. But I don't need to refer to it here. I know that paper beats rock, scissors beat paper, and rock beats scissors. And this last thing is for tie. And then finally, we have commutativity, right? And you'll notice we have fewer methods here than we have actual combinations, right? Because of the commutativity fallback. Essentially, what that says is if I have a shape here and a shape here, I know that I haven't dispatched to anybody else because I got to this fallback, right? All I know here is that I have a subtype of shape and a subtype of shape. And that is a less precise, it's a less specific method than any of these, right? In this case, I have exact leaf types. In this case, I have exact leaf types, same here. And here I know that these are two of the same type, which is more specific than two of any type. The way we dispatch in Julia, the way we overload in some languages, is we choose the most specific method. And the most specific is just across all of the arguments, not just the first one. That's how it works in C++ and Python, is we have single dispatch. You can do a visitor pattern to recover or double dispatch to recover some of this sort of dynamicity. And it's not really a strong weakness, right? You don't encounter this pattern as much as you would really think. A lot of Julia code is single dispatch. But this is sort of fundamentally how Julia works. You define a bunch of fallback functions, and then for the ones that you know you need special care for, you define very specific methods for them. And so what does that look like? Here I have a nice grid. This is argument 1 on the bottom. This is argument 2 on the left. And we can see how many methods I've saved here by using the abstract types and by using this diagonal dispatch here, essentially. Why is it called diagonal dispatch? Well, this is this type T function or method, right? And if I hover over here, you can see type paper dispatches to type T. And it's the same with rock. When you have 2 rocks, you dispatch to this diagonal dispatch thing. And same for when you have 2 scissors. The reason it's called diagonal dispatch, it doesn't look that way textually, but it's because of this square right here. Because it looks like this on the diagonal. This here is the commutativity one. So when I have a rock, or when I have a scissors and a rock, I haven't written this down here, right? I wrote the rock and the scissors, but I didn't write the scissor and the rock. So this dispatches through the commutativity fallback. It swaps the arguments, and then it gets back to rock and scissors, and rock wins. So these 3 are covered by that commutativity. This is the diagonal. And these 3 are the actual rules of the game that we have defined right here.
Implement one of the types. If you have just only the fallback and not the normal one, does it just loop forever?
You don't have the fallback.
If you have the fallback, but you don't have the original.
Oh, you can yes, you can dispatch forever. Let's see if we do play 2 of a type shape, B type shape equals play 2 of BA. And I'm going to call it. I'm not going to try to abuse my little vibe-coded tool here to graph what that ends up looking like, but I will call it on rock and paper. And warning, detected a stack overflow. Program may be corrupted. It detected that pretty quick, actually. It didn't wait very long. I might have to reload my REPL now, but worth it. Yeah, this is one of probably the only really easy ways to get a stack overflow in Julia is when you do this swapping of arguments without sort of the knowledge or guarantee that you are going to hit a base case eventually. You can go pretty deep. The promotion system that I mentioned earlier does quite a bit of finagling around before it hits the base cases. And the promotion system can stack overflow in certain edge cases, even though it's built into Julia essentially. This is sort of one of the prices that you pay for the flexibility, but it's possible to do this kind of thing in a lot of languages. Type checkers in general often face this sort of issue. You can do this, by the way. This is the dispatch display function, which is if you do using glmaki and using dispatch display, you should be able to do this exact same thing. I'll do a few more here. If you're on certain machines, glmaki does not work. It's like, if you're doing GPUs through WSL on Windows, glmaki just simply can't cope. In which case you may be able to use other Maki backends. Maki is one of our 2 big plotting libraries, but it's not that big of a deal in the end. You can extend to a 4th type here, and that'll just extend us to a 4x4 grid with the dispatch display. I want to do one of the big dispatch displays, so let's see. Include.
No, I mean, these are something running.
Why am I not getting tab completion? Oh. So I went too far.
So this was the display. It's just added.
Oh no. I have made a huge error.
What was that?
Okay. Let's see. All right. These are the two
Types and dispatch.
views on the plus function on two arguments, the arity2 plus operator. So arg1 again is on the bottom, arg2 is on the left for both of these. And you can see that we actually do quite a bit of multiple dispatch here, right? We don't have, a pattern that is super easy to express where, you might dispatch on arg1 and then within you might overload on arg2. You have some pretty complex patterns. Like for here, this is the plus of big float and uint32 dispatches to this specific method that is a C call to the MPFR library for big float numbers. Here we have big int plus big int, and that maps to MPZ, which is the library, the C library for big int numbers. You also have things that all this gray here, you can still add these because on the left-hand side, these are all numbers, but this is when you get into promotion. So you see if I try to add float 32 and int 128, what this first does is it dispatches to the abstract number method, and then it promotes from there. And then the hope is that after the promotion, you'll end up with two of the same type, and that will decay back down to a specific method like this MPFR one, this MPFR one, or this MPZ one. This is another big int, big float one. You have this band. This is the diagonal dispatch right here, where these are the bit integers. This is rational numbers over here. So rational of int 64 and rational of int 64. And then these are the complex ones down here. So you can see this is not super easy to express simply. This is the same thing, but for all possible arguments in the Julia type system that support addition. So you can see that most of the time this doesn't work. All this white space, nothing happens here. This is a method error. For instance, if I try to add an int32 and a dates.second from the dates standard library, I can't add int32 and dates because who knows how many seconds that is in 32s, right? So we get these big areas where nothing happens. And then here, for instance, this entire block, this is the dates library. We have this weird little diagonal dispatch thing going on here. This is the numbers right here. That is on the left-hand side of my screen. These two giant bands are the absolutely cursed library chain rules core, which anybody like Katie who has dealt with a lot of autodiff knows that is a painful library. So you get these giant bands, and what this is that dates.nanosecond and added to chain rules core.no tangent dispatches to something that just returns the nanosecond. And that entire band is what that does. So yeah, this is one way to visualize Julia's multiple dispatch. We can also do this in 3D, but I don't know that I have something in front of me well, I guess I can just dispatch display plus numeric types, I think. Numeric types. What I'm doing here is I'm saying I want to restrict myself to the numeric types for my dispatch display so I don't make it sad. And then I want to do all three arguments as numeric types. We done at 5 or 5:30?
5.
Okay. So you can see here, this is the addition of 3 numbers, and there isn't really anything happening here. That's because Addition of three numbers is just addition of two numbers twice. Except for there is one spot where for some reason adding, you can see that in the middle through the transparency, adding three big ints is better to do as a specific instance. Right there. There. So even in cases where you think, oh, why would I ever need to specialize on adding three numbers when I can just do it twice? There are real reasons to do this, right? It's potentially more efficient to add three big integers in one go than it is to do it twice. This is true, for instance, for matrices, right? When you multiply three matrices, there are some algorithms for the matrix triple product that are faster than multiplying the matrix twice. And this is the key idea behind multiple dispatch. It's certainly not perfect. You can easily run into a lot of issues, right? Where a lot of people are sort of creating what we call ambiguities, which I'll talk about in the next session. And it can be pretty complicated to get things right. But for the purposes of numerics, it can often be super key to get high performance. And I believe it's now time for dinner.